Okay, so since everyone is back, we can start again. So we're happy to have Geoffrey, who will speak on the interaction reconstruction in scintillator detectors for PET imaging. So thanks a lot for being here, and the floor is yours.
Thank you very much. So good morning, everyone. Thank you for the invitation. So as it has been said, I will talk about gamma ray photon interaction reconstruction. So for positron electron tomography imaging, which is medical molecular imaging for medical purposes. And I use here a deep learning approach with uncertainty quantification to try to make to do this reconstruction. So first, I will start with a few words on PET scan, PET imaging. So positron emission tomography is a molecular imaging modality that is used mainly to for diagnostics. So actually, it consists in injecting radioactive tracer into a patient associated to a sugar. So that the sugar will focus on a specific part of the body, so mainly part with evolutions, biological fast evolutions, such as cancer or neurological pathologies. And then it helps to make some diagnostics to understand the evolution of the biological process, and then to help for treatment, development of new treatments, and know what is the kind of treatment that is adapted. Actually, so this modality of imaging is very interesting and very important and in development over the past few years. And now there is a challenge, that is the improvement of the spatial and temporal resolution of this kind of imaging modality. Actually, we can understand this. It is already efficient, but the problem is that we have to inject a radioactive tracer into a patient. So it's a problem because we have to limit the dose that we inject. So we have to be very efficient in signal to noise ratio. So that's why we need new instruments and new processing for this instrument to help achieving better signal to noise ratio and better resolution. So to understand how it works more precisely, the radioactive tracer is actually a positron emission radioactive element, and the positron are emitted by this element and then will annihilate in the body of the patient. And this annihilation produces gamma ray photons at about 180 degrees apart the annihilation. And these gamma ray photons can go through the body and then be detected in some detectors that are around the body. Actually, for the moment, if we have detectors that can distinguish gamma ray photons in coincidence, but that are not so precise, we can know the line of annihilation, and by using several elements, we will have several lines of annihilations, and then we can reconstruct at the intersection what is the position of the source. But now what we want to do is to exploit the fact that the speed of light is limited, very fast but limited, and if we are precise enough, we can also, by using the difference of time, of arrival time between the two detectors, we can try to be more precise on the line and to know, okay, for this event, we should expect that it happens in this area, more precisely. And the same for several events. So by knowing the time of light, we are more precise event by event, so we need then less events in the list to be able to localize more precisely the position of the annihilations and the position of the sources inside the body. So that is very important because we will be able to keep the same resolution by reducing the exposure dose for the patient, and then we can for instance, propose this modality approach, so PET imaging, also for children. For the moment, we cannot propose it to children because we cannot inject high doses to children, or for pregnant women, or also for other patients that we would like to follow more regularly. And so to apply this PET imaging more regularly to this patient and having a follow-up diagnosis for this patient. So actually, the coincidence time resolution in state-of-the-art is 215 picoseconds. It corresponds to a spatial uncertainty of 3.2 centimeters, so event by event. So it means that this Gaussian is 3.2 centimeters, which it seems to be quite nice, but the problem is that 3.2 centimeters, it can be the size of an organ, so it's not so precise. What we would like to do is to achieve 1 order of magnitude reduction of the time resolution, so it will correspond to 1 order of magnitude for the spatial uncertainty, so to have about 3 millimeters. So that's why there are several challenges. The first one is the development of an instrument that is able to achieve this kind of temporal resolution. And there was a collaboration, previous collaboration between several partners to develop a new kind of detectors that is able to exploit fast photons, fast Cherenkov photons inside the detector. So the main principle of these detectors is that when it's a scintillator detectors, so when a gamma ray photon interacts inside the scintillators, it will produce Cherenkov photons. So Cherenkov photons is due to the fact that it will produce an electron that is faster than the speed of light inside the scintillator. And these Cherenkov photons are emitted instantaneously, so with a time that is at the order of magnitude of a picosecond. And then there will be other photons that are emitted, scintillation photons, that are emitted later. And all of these photons are then optical photons. They are detected using a specific photocathode, and it produces signals that are then acquired by the detector. So by using this fast photon, we are able to have a right datation, a correct datation of the interaction. And using the scintillation photons, it helps to bring also information to obtain the other properties, so the position and also the energy. So as I said, the targeted resolution of gamma interaction reconstruction inside the detector, it would be some millimeters, and then to obtain a coincident temporal resolution of dozens of picoseconds. The main problem with this is that the signals that are produced, they are very complex. I will explain why later. They are very complex to analyze, so that's why there is also another challenge, which is the signal processing to reconstruct the parameters of interaction, of the gamma ray interactions. So here we have a pipeline where we want to model and simulate the detector to represent the detection chain, so that there is a modelization to understand how the processes happen inside the detector, so the gamma ray interaction, the scintillation process, the production of the signals. And then by using these simulations, we can train a machine learning algorithm to try to reconstruct the interaction parameters. So as I said, the gamma ray interaction parameters, it's the 2D position, or here 3D position of the interaction in the crystal, time of interaction, energy deposited, and hopefully the multiplicity. For the moment, I will focus mainly on the 2D position. It's the current work that has been done for the moment, and then future works will focus on the 3D position, time of interaction, and also energy deposited. By using these parameters, it will be then transferred to imaging reconstruction, so for an application of a complete scan of the body, and then to be able to localize the sources inside the body. So, as I said, we use simulations in order to produce data that will be able to, that will help to train a machine learning algorithm. Why do we need simulation? It's because by using the instrument, we do not know what is the exact position inside the detector. But using simulation, we control everything, so we know what is the position. So firstly, we have a gamma ray photon interaction inside the detector at some position, 2D position x and y. It produces Cherenkov and scintillation photons, so optical photons that will travel through the detectors. So it's a kind of fireworks inside the detector. And this optical photon, then they interact inside the photocathode, and they produce signals that are registered in lines. So you can see here the lines of the detector. And each signal that you see there corresponds to a signal along one line. Actually, we can see here that if we have some lines that are activated in some region, we can know more or less precisely the Y position in here. So if we know that there are these lines that are eliminated, we know that the interaction is in this region. And then we registered also the right and the left signals. So by using the difference of time between the left and the right signals, we can know what is the position approximately along one line along the X position. But you see that it's very complex because we have several optical photons which are not the initial interaction. It's just actually spread around the initial interaction. And also, the signal can have what we call pileup. So if there are two photons that are detected on the same lines, the signal will add up. So it's very complex to process. Then we have a first preprocessing step because by using this signal, we can extract some variables of interest that are expected to be related and correlated to the interaction parameters. So that's are the signal that we will use as an input for the neural networks. So I mentioned here the complexity of the signals, but there are also some phenomena that are to be considered. The first one is that all the physical processes inside are completely random. So that's why we use simulations. So here, we have randomness according to the gamma ray interaction. Is it a Compton interaction or photoelectric interaction? We have randomness in the production of scintillation photons and Cherenkov photons, and then their path inside the detectors. Randomness in the acquisition of the signal because there are noises, because of the readout, electronics readout. Here I said that we extract some variables from this signal to be faster for the neural network, so we can have a loss of information. So there is a lot of uncertainty, so random fluctuation uncertainty, systematic uncertainty, and that's why we know that we won't be able to reconstruct very precisely always the position of interactions. So that's why we need also to have a neural network that is able to provide uncertainty quantification for each event to be able to assess the precision of the reconstruction. So, as a summary for the machine learning approach, our objective is to predict the 2D coordinates of the gamma ray interactions. The input, it's the preprocessed variables that are extracted from the complex signals, these ones are the output of the simulation and the preprocessing step. The output of the machine learning, so it will be the 2D gamma interaction coordinates that we can know because we use GM4 simulation, so we can store this interaction coordinates event by event. So a conventional machine learning approach would be to, for example, to build a neural network with some parameters that will output the x and y position with two outputs. So for instance, here we can use a multi-layer perceptron because we have 23 variables as input in order to capture the complex relations between the input and the outputs. The expected benefits of the neural network approach is that we can learn possible complex nonlinear mapping between the input and the outputs. So conventionally, what we would do is to build a neural network using a mean squared error loss function to train that we have to minimize to find the parameters that explain the data. But a limitation of this approach is that the prediction is seen as deterministic. If we have one specific event, we will have one answer. So there is no uncertainty associated to the prediction. So that's why we have developed a new approach that will help to predict also an uncertainty. So we have to adapt the model and the loss function to estimate uncertainties under reconstruction. So that's why we use what we call density neural network. I will explain what it consists later. And then we want also to consider some constraints that are due to the geometrical limits of the detector. So for instance, one constraint is that we know that the interaction is inside the detector and not outside. If we observe the signal, it means that the gamma ray interactions occurs inside the scintillator volume. So we know that there is no possibility to have a position of interaction that is outside the detector. So the model adaptation is the following. We modify the last layer so that we do not predict only two outputs, not only the position of x and y, but also an uncertainty, a parameter that represents the uncertainty on x and y, event by event. And we adapt also the loss function that considers these four outputs to produce some uncertainty. So we use a truncated Gaussian likelihood hypothesis. So it helps to obtain, to integrate the sigma here that could represent the uncertainty, and also the truncated part, it helps to indicate that we expect the events to be between the limits of the detector, so here it's minus 30 millimeters and 30 millimeters, and we know that we do not expect interaction outside these boundaries. So then we can write the likelihood of an event to occur at some position x if the signal that is registered with S, and here is the truncated Gaussian likelihood that is represented. So you can find here the truncation part, and here the Gaussian likelihood, the classical Gaussian likelihood. So based on this, we can derive the likelihood of the parameters according to the data. So it consists in considering all the events of the database independent and identically distributed. So we can say that the likelihood is the product of all of these individual likelihood according to all of the events. And then by using this, so if we assume that x and y, the two positions are independent, we can now write the loss function as the logarithm of the likelihood, negative logarithm of the likelihood, to transform the product as a sum. So here now we have a sum of all of the probabilities that are defined here, not the probability but the logarithm, there is a logarithm that is missing here, the logarithm of all of these probabilities. So here we obtain a new loss function, that is this one, and actually, it seems to be, it's not so complicated. We can recognize here the part that corresponds to the normalization factor corresponding to the truncation, and here it's the classical Gaussian likelihood. Actually, one comment here is that we can find the classical mean squared error if we assume that sigma is always constant. There is no truncation, so we do not have this part. Sigma is constant, so we do not have this part, and this part either. So we find again z minus mu, so the prediction, squared. So it's the classical mean squared error. Now we have all of these terms that help to consider also an uncertainty that is what we call heteroscedastic. So we expect the uncertainty to be different event by event, and also this truncation. Another comment is that we have a loss function. We have to ensure that we have the good properties so that we can exploit it for neural networks. The main property is that all operations should be differentiable. And it's the case. Actually here, the logarithm is differentiable if we have something that is positive inside. Here, phi is the cumulative distribution function of the Gaussian, so we can differentiate it easily. It's the Gaussian, the classical Gaussian. So all of this can be exploited by usual frameworks such as TensorFlow or PyTorch to apply automatic differentiation. So the second comment is that by using this, we can access event by event, the uncertainty for the position. So we can have a prediction of the position with mu and the associated uncertainty with sigma. And we will show that we can use it, for example, to have a weighting proportional to the inverse of the uncertainty that is predicted. So then, by using this search function and these new neural networks, we can train a neural network based on the simulation here of a cube-shaped source, uniform, that is uniformly distributed in front of the detector, so that we have several events that are simulated with energy deposited. So we have this simulation, and also two testing configurations. So we have simulated a grid of sources to visually represent the performance of the reconstructions. I will show this in the results. And also a uniform 511 kV source to evaluate quantitatively the performances. And for the comparisons, so I will apply a baseline method that do not use machine learning. It's just based on the expert's knowledge. A neural network that is trained with the classical MSE, so the classical approach with no uncertainty prediction. The neural network trained with the truncated Gaussian likelihood, so the ones that I have presented just before. And finally, the same network, but I have weighted the events according to the uncertainty, so to show the impact of the uncertainty to the event reconstruction. So here, as a result, here it's the simulated grid of sources in front of the detector, so it's the target we should reconstruct. So there are hundreds of thousands of events that are simulated. And at each position, about 300 events have been detected. So event by event, we try to reconstruct it. As you can see here, is the reconstruction of the baseline method. So we can see that we see the grid, but the predictions are spread, and also we can see dead areas. So the baseline method is not able to reconstruct interactions that are close to the edge. The classical MSE approach with a neural network, actually it does not seem so much better. It does not reconstruct also events close to the edge, and the reconstruction are spread as well. By using the truncated Gaussian likelihood, we see that actually we are able to reconstruct events close to the edge. The main problem is that we are less precise, and it's understandable because the photocathode is not, does not cover all of the detector. There is a line where the photocathode is not present. But the main problem is that here we can see that the events that are close to the edge, they pollute the part here, because there is an overestimation of events at this size here, for instance. And here, we do not have this folding effect and no dead area, so it's better here. And then we can also exploit the fact that we have the uncertainty, so we can ponderate the uncertainty. And we find here that events that are far from the sources, they are more uncertain because they are ponderated with a lower weight. And now we can find more precisely the grid that has been simulated. So here it's just mainly a visualization, and then we can try to quantify more precisely the precision of the detector. So when we use here a uniformly distributed impact on the detector, so we can see here the reconstruction of a uniform source. So we can see the same shape, so dead areas here by using the baseline and the conventional MSE. And if we use the truncated Gaussian likelihood, there is no dead areas, and we have a better estimation by using the weighting approach. So now we can, by using this test configuration, we can try to quantify more precisely the resolution. So here we want to represent the spread of the predictions if we know the right position of the interaction. We want to quantify what is the spread of the prediction around this around the right positions. So here the baseline method, we can see that there is a high spread of the prediction here in the large area, so more than 6 millimeters of uncertainty, and at the position, so in the center of the detector, there is at the best between 2 and 3 millimeters of uncertainty, of error, sorry. The conventional MSE approach, we have the same features. Actually, the area where we are less precise, more than 6 millimeters has a lower surface, but still in the middle we are between 3 and 4 millimeters of precision. Using the truncating Gaussian likelihood, we have the same effect, but by using the uncertainty, we can now ponderate and apply a weight that is higher for more precise events and lower for less precise events. So we can recover here a better precision, and in the middle of the detector, we have between 1 and 2 millimeters of error, which is better and corresponds to the objective. So here, it's actually another representation. So before, what I represented it was the spread around a known interaction, and now here what I represent is that more what we would call precision. If we have a prediction at some areas, what is the distance to the true interaction? So it's a kind of inversion between the conditional probability. Before, I represented the map where we know the interaction and we represent the spread of the prediction. And here, we know the prediction and I represent the spread of the true interaction. And we can see here that in terms of precision, the Bayesian method seems to be very worse than the other method. Actually, the precision is more than 6 millimeters in the Bayesian method. For the conventional MSE, it's again between 2 and 4 millimeters. And applying the weighting by using the uncertainty, we recover between 1 and 2 millimeters of precision. And when we are far from the center of the detector, we have the effect because of the uncertainty, which is higher at this position. If we focus on the X and Y positioning separately, so we can see here that using the Bayesian method, actually the standard deviation on the Bayesian method is 8 millimeters on the X coordinate, which is the coordinate that is the most difficult to reconstruct. And by using the truncating Gaussian likelihood with the weighting parameter, we have 2.5 millimeters. So which is quite correct according to the objective. For the Y coordinates, which is here, we have a better resolution. We have 2 millimeters by using the weighting. So a last validation is the validation of the uncertainty, because we predict uncertainty, but maybe the neural network can predict uncertainty that is not relevant. So we have to verify if the uncertainty is correctly predicted. What we use is what we call coverage plots. So the coverage plots, it represents actually the probability level of a certain interval, so an interval of positions. And then we measure the frequency of real test data that falls into the interval that is predicted. So for example, if we have an interval at 60%, we compute for all of the events the interval at 60% for the position, and we measure, we count the number of times the right position was inside this interval. What we expect is the right curve, so the diagonal curve, which represents a perfect calibration. And in blue, it's the calibration that we obtain with our model. So we can see here that for both positions, X and Y, we obtain a quite correct calibration. So it means that we can trust the uncertainty. Actually, it's a bit overconfident slightly overconfident at this position, because the blue curve is below the red one. So it means that, for instance, when we have a probability level at 40%, it represents 35% of the events. So we are overconfident here, and a bit underconfident for these probability levels. But still, it's still relevant for the exploitation for the tape reconstruction, because now, since we are able to affect event by event an uncertainty, we can know what are the events that we should discard because they are more uncertain, and what events we should keep, or we can apply a weighting approach to try to improve the signal-to-noise ratio. So as a conclusion, we have these new detector systems that was in development for the ClearMind project. A fast scintillator detector. We have had a need for specific processing of the signal because of the complexity of the signal and the fact that we need the uncertainty associated to the prediction because of the intrinsic randomness of the phenomenon. So we used a density neural network with an adapted loss function to estimate the uncertainties. By using these neural networks, we had a recovery of the dead areas close to the edge, so that means we can exploit a larger surface of the detector. And also, we were able to predict the uncertainties so that are consistent and reliable, and we can exploit it for future reconstruction in real PET system to increase the signal-to-noise ratio. So the next step will be to apply this kind of techniques not only to predict the 2D positioning, but also the 3D positioning, the depth of interaction, the time of interaction, and the energy. So the next step will be carried out by a specific project that is funded by a national research agency with several partners, and then to apply it to PET image reconstruction. So the next steps are starting now, and we will present the results later. So thank you very much, and if you have any questions, I can answer.
Thank you, Geoffrey. So do we have questions for Geoffrey?
Hi, and thanks for the talk. So I have a question regarding your neural network, yes, so your model. So how do you choose the hyperparameters of your neural network? Or in other words, how do you know that the model that you chose is appropriate, is the right one?
Is the right one? Actually, there is no specific method to know that we have the optimal model. What we know that we obtain results here in terms of precision that seems to be actually satisfying according to our objectives. Maybe there are ways to improve it. We can improve the model, but already actually we use the multi-layer perceptron with 4 or 5 layers and 500 neurons per layer. So it's quite complicated for the moment. So it's able to represent a very complicated function. So maybe we should have we could complexify the network, but I think it would not really improve a lot the results. We have tried several neural networks, but these results are the best we obtain. We could maybe improve the results by using the whole signal, not only the preprocessed variable, but the whole signal by using the convolutional neural network. But the problem is that it's longer to train. We need many more data. So that's why we first focus on this. And in the next step, we would use also the whole signal to try to keep the whole information and maybe obtain a better resolution this way.
Okay, thank you.
Thank you for the talk. I have a question regarding the loss.
Yes.
Why do you use the truncated loss instead of a simple heteroscedastic loss?
Instead of a simple Gaussian
Heteroscedastic loss?
Simple Gaussian heteroscedastic loss, for instance, without the truncated part.
Yeah.
Yes, actually, we tried also the Gaussian, the classical Gaussian without the truncation, and actually by using the classical Gaussian, we had also the problem of on the edges. The neural network didn't want to predict something that is close to the edges. And actually, I can show you a small scheme of this. If we know that interaction cannot occur outside the detector. So for example, here the limit of the detector are in black. If we have a Gaussian hypothesis, actually we expect that there is a probability to have something outside of the detector. We assume that it's possible. Actually, it's not possible by physical knowledge. But since then, all the interactions happens inside the detector. So here, the Gaussian does not observe something outside the detector. So if you have a classical estimation, you say, oh, the mean is not here. We should have something that is somewhere here. So by using the Gaussian hypothesis, we tell, okay, there is nothing to see here, so we have this truncation, the probability is 0, and then by using the truncation, we know that the neural network is able to predict something that is close to the edge because there is no this repulsion effect due to the fact that we do not observe something outside of the detector. So that's why the truncated Gaussian helps to predict something inside the detector.
Okay, thank you.
D'accord.
Thank you for the talk. I was going to ask you, you assume that the variance is diagonal, and you even assume that the x and y are independent, so in an even stronger assumption. Would not assuming this and having like a covariance, have you tried that, or do you think it's like a good assumption to have?
Actually, yes, we have tried also to apply a covariance, but the problem is that it's more complicated to have a truncated Gaussian hypothesis with a covariance, because it's more complicated to represent in the loss function. So we have tried without the truncation, and we have also applied this. So for some events, we observed actually a covariance that is predicted, and actually we had to balance between the fact that we do not recover the edges of the detector and the fact that we have a covariance. So we prefer to use this one, but it's true that it would be better if we could have this covariance also to implement. Actually, if we want to predict the covariance with a classical Gaussian hypothesis, we just have to set another output, which is the covariance between which is one parameter, and then we can write the classical likelihood and derive it and differentiate it. So it's possible, but with the truncated part, it's not compatible for the moment. So maybe with some specific work, we could try to approximate it.
So the truncation, like the formula for the truncation, would be a bit different.
It would be different and maybe more complex to implement. I don't know if it would be possible to differentiate it, but we should think of it. And actually, for the moment, the results, it was satisfying with this, but we have a postdoc who would work on these next steps. So maybe we will try again if it's relevant to put the covariance effect.
Okay, thank you.
Thank you.
Any more questions? Okay, if not, we can thank Geoffrey again.
Thank you.